Hello, in this presentation I will be presenting about Mary CPU project, which is a simple representation of assembly language. I will be covering mainly three things, which are architecture, assembly, and simulation. Going from transformation of C code or C language code into assembly code, writing the hex numbers and representation of this assembly language, and then moving to simulate it in the program. Before implementing this program, we need to know some general information and also specific details about Mari architecture that I'll be presenting in this slide. Okay, so there are 16 bits in this format, which is hexadecimal from 0 to F, which gonna give us or generate us more than 4,096 data as a placeholder for our information and instruction. Also, we have the AC accumulator, which we can call it a middleman between the memory and each instruction, facilitate read and write back from LAU to the AC, which gonna facilitate our operation. Also, we have the BC. The BC is incremented after each fetch program or each fetch cycle, which we're gonna explain it in the next slides. Because after the fetch we have the encoding and also we have the execution, so we need a new one or a new block for this. We have also the instruction register, which is simply executing the instructions, which is divided into two parts. We have 4 bits for the opcode or the function, and also the lower part of it, which is 12 digits for the address. And for each one we can write as the first number or digit that determines the opcode or the function, and the lower digits determine the address. We have the memory address, which we can write and read from it, donated as MEN parentheses. And lastly, we have the simple instruction set. We have the main ones, which are load, store, add, jump, etc. And we're gonna explore them more in the next slides. In this slide, we have two parts, which are an instruction set, and in this setting, we have 4 digits for each command or for each operation. The first digit it is for the operation or will determine the operation. For example, we have number 1 for load and number 2 for store and so on. However, for halt, we have only like one number, which is 7,000. But the previous ones, they can change into, for example, jump 5111 or so on, or whatever numbers. It's important just the first digit in the system. And for the last one, we have 4 like 8 and 4 and 0 for skip code, which in which I have a problem. I will discuss it later. And for the state machine, we have 4 also operations, which are fetch, loading instruction, and also decode, and execute, and memory. They will appear later in the simulation. For each block or for each instruction, we have these 4 states in which the operation or the function run. Okay, Mari ACM is a simple representation of assembly code. We can translate the C language code into the ACM. For example, for each part, let's take I equals to 0. We can do it like load 0 and store I. This means it will link 0 into I, and so on for the lobe and for the body However, like I discovered something here which I can delete the jump body if I change the skip count into other demand other than 000, because we know that it's not just 000. We have also uh, 800 and also 400. One of them will work here and it will automatically jump into the other part, but I've kept it the same way as the professor did, which is using two jumps instead of one. Here we can see the function of the first digit manifested clearly. For example, if we take the first one, which is 1019, it will appear that this instruction will be uh, load, and for the second one, which is 2, it is for store, and the third one also it's load, but with a different thing. What is difference? What's the difference between the first one and the third one is that the first one is located at the accumulator 0 and the second load accumulated at the address 40 because of the difference of the addresses and numbers. Moving forward, we have also the 4013, which is for subtraction, and the next after that is the 8, which is for skip count. And also notice that we can do like 800, and also we can do 8800 for the other thing or for the other inequality, and also we can do 8400. We have like bigger than, smaller than, and also equals, skip if. So this function is skip if, and we have 3 operation in this function. Moving also, we have 5011, which is for jump, and the last thing we have 7000, which is only one number, which is for hold, and the data stored without the first digit, because they don't need an operation or an opcode for that. They are just normal data and we can store them directly. Okay, here we have the simulation of the hardware using software. In this system, or in this picture, I colored the instruction for illustration. And first of all, we have the PC, which is the address of current instructions, following by numbers according, like in the order, like they are order from 0, 1, 2, 3, 4, and explaining each or show each one of them. The first, like the CPU state, have 4 cycles per each address or per each machine state. These cycles are fetching, decoding, execution, and memory. Each one has its own binary number, 001 for fetching, etc. So we also have the clock here, which is colored by the orange color, and also always rising and falling for each cycle. Uh, Starting like at the beginning of the cycle, it's in the rising, and then it's falling. And for the memory writing or memoir, it only goes rising in the storing instruction, especially and only in the execution part. In the execution part and in the storing, we have the rising of the memoir, and also we have the memory data, which are dividing both receiving or reading, and the other is giving or something like that. We can see that the memory data has a block for fetching and decoding for their own, and also the other two for their own as a block here in the system. And also we have the increment PC, which only rising while fetching. And lastly, we have the instruction registers holds the decoding instruction being executed. These issues really pushed me for discovering new thing and fixing my problem. The wrong skip code. I initially wrote a wrong skip code, which is 8800, and then I discovered that while writing this, it will hinder me later on in the process. So I reverse it by writing 8000 for the skip code, which is enable me to make the I less than n if AC is negative in this part. So I just change it to 800, which is correctly skip the jump and going for the loop. The second problem is downloading the package or the iForlog and Linux system into my account, but this problem was solved by consulting one of my senior friend in this matter who helped me a lot in it. The third part is like writing the hex numbers. It was really troublesome for me since they are a lot and I wrote more over that it needed to be, then I deleted some. Like I repeated some instruction or hex number because I'm not familiar with this matter. The last thing is the jump. We have two jumps in the system. One jumps for the end and one jumps for the body, which did not make sense for me at the start. So I searched for it and I discovered that the some system will go immediately into the loop. It does not need a jump body. It only needs jump in if it's ended, but it will go just immediately to do the body, and we do not need the second jump. We only need the first jump. But then I abided by this uh, file that sent to me, and I made two jumps instead of one and wrote the entire code accordingly. Okay, so there are five takeaways from this project. Number one, how a CPU actually works. This is astonishing for me because uploading or mimicking the hardware using the software is really a good thing to learn. Seeing, fetching, decoding, executing in this part was really good. And also, assembly is precise. Each instruction, each number, if it's wrong, it will give you another output. Focusing on the first digit part will generate you or will give you error in the matter. The third thing is that the hex numbers, which are the main representation of this project, is consider or consists of two things: opcode plus address. The opcode determines the function or the instruction of this method, and we can write any number after that for the address, but we need to follow some rules and instructions in this matter. Fourth one is simulation reveals the truth. I really like it, the wave or the GTK wave that show me exactly which signal went high and which went low, and I know more about this program and this project using the waves. Lastly, small ICA and deep insight. With only few numbers, we can generate multiple stuff, and doing that algeometrically and mathematically using codes and functions. Uh, Thank you all for listening. See you.